In previous videos, we looked at general aspects of atomic theory and atomic structure. In this video, we investigate the differences between atoms of different elements and characterize them using atomic numbers and mass numbers. We are also introduced to the concept of isotopes. So we start by asking the question, what makes an atom of one element different to an atom of another element? The answer lies in the composition and number of the subatomic particles, and more specifically the number of protons. Specifically, the identity of an element is defined by the number of protons in the nucleus. All atoms of an element have the same number of protons in the nucleus, and the specific number of protons is different for different elements. So for example, all hydrogen atoms have 1 proton in the nucleus, all helium atoms have 2 protons in the nucleus, and all lithium atoms have 3 protons in the nucleus. And it is no coincidence that hydrogen, helium, and lithium have atomic numbers of 1, 2, and 3, respectively, as the atomic number is actually equal to the number of protons in the nucleus. And remember that the symbol for the atomic number is Z. If we look at some other common elements, we see that all fluorine atoms have 9 protons, and you'll find fluorine as number 9 on the periodic table. It has an atomic number of 9. All fluorine atoms also happen to have 10 neutrons in the nucleus. All sodium atoms have 11 protons in the nucleus, and sodium has an atomic number of 11, and you'll find its number on the periodic table as 11. It turns out that all sodium atoms happen to have 12 neutrons in the nucleus. All aluminium atoms have 13 protons in the nucleus, and aluminium is the number 13 on the periodic table, and all aluminium atoms happen to have 14 neutrons in the nucleus. All phosphorus atoms have 15 protons in the nucleus. Phosphorus is number 15 on the periodic table, and it has an atomic number of 15. And it turns out that all phosphorus atoms happen to have 16 neutrons in the nucleus. So while the number of protons in a nucleus defines what the element is, there are no hard and fast rules about the number of neutrons. This is a representation of a carbon atom. Carbon is number 6 on the periodic table and has an atomic number of 6. It therefore has 6 protons in the nucleus. Now, since an atom has no net electrical charge, the number of electrons equals the number of protons, so therefore a neutral carbon atom also contains 6 electrons. Most carbon atoms happen to have 6 neutrons, but a small fraction of carbon atoms contain an extra neutron, taking the number of neutrons to 7, and an even smaller fraction of carbon atoms contain 2 extra neutrons to give them 8 neutrons in total. Unfortunately, there are no set rules for determining the number of neutrons in an atom, and we simply cannot use the atomic number or the number of protons to work this out. A second number, called the mass number, is needed to help. So if we go back to our carbon atom with 6 protons and 6 neutrons, we call this atom a carbon-12 atom, and it takes its name from the mass number. And the mass number is equal to the number of protons plus the number of neutrons. The number of protons and the number of neutrons is equal to the number of nuclear particles in the nucleus, or equal to the number of nucleons. So in this particular case, 6 protons, 6 neutrons, a total of 12 nucleons. It takes the name carbon-12. Carbon atoms with the extra neutron have a total of 13 nuclear particles, or 13 nucleons, and take the name carbon-13. And carbon atoms that have 8 neutrons in the nucleus have a total of 14 nucleons and take the name carbon-14. Atoms of an element that differ in the number of neutrons, and therefore mass, are called isotopes. Carbon-12, carbon-13, and carbon-14 are said to be isotopes of carbon. We can represent different isotopes of elements by using this shorthand notation, where the chemical symbol of the element is written with a preceding subscript representing the atomic number, which is the number of protons in the nucleus, and a preceding superscript representing the mass number, which is the total number of protons and neutrons. So the carbon-12 atom has 6 neutrons and 6 protons, and therefore has a mass number of 12. Carbon-13, with 6 protons and 7 neutrons, has a mass number of 13. And carbon-14, with 6 protons and 8 neutrons, has a mass number of 14. These chemical symbols can be shortened even further because we recognize that once we write down the chemical symbol C, we are actually talking about the element carbon, and all carbon atoms have 6 protons. And so the preceding subscript of 6 essentially becomes superfluous, and we can write down carbon-12, carbon-13 and carbon-14 isotopes in this way. This table shows the isotopes of some common elements, and among the 92 naturally occurring elements, there are 286 naturally occurring isotopes, and there are only 23 elements that are monoisotopic. That is, they only have one naturally occurring isotope. Some common examples of monoisotopic elements we've already come across include fluorine-19, sodium-23, aluminium-27, and phosphorus-31. Most chemically pure samples of elements contain mixtures of isotopes which occur at varying abundances. So, for example, we can see the three isotopes of carbon, carbon-12, carbon-13 and carbon-14, have relative abundances of about 99%, 1% and 0.01% respectively. The actual masses of each isotope are shown here in atomic mass units. So this gives the average mass of a carbon atom, when the relative abundances are taken into account, being slightly above the mass of carbon-12 at 12.0107 atomic mass units. And this is the atomic mass that you will find on the periodic table under the chemical symbol for carbon. So the atomic mass that appears under the symbol of an element in the periodic table is actually the average mass of all the available isotopes when their relative abundances are taken into account. Taking a look at a few other isotopes, we can see here the isotopes of hydrogen are given their own special names. For example, the hydrogen-2 isotope is known as deuterium, and the hydrogen-3 isotope is known as tritium. The relative abundances of deuterium and tritium are quite small, with only 0.02% of all hydrogen atoms being deuterium atoms, and a vanishingly small percent of all hydrogen atoms are tritium atoms. Now, a common element with an appreciable amount of more than one isotope is chlorine. We can see that about 3/4 of all chlorine atoms are chlorine-35 atoms, and about 1/4 are chlorine-37 atoms. When we take into account the average atomic mass, taking into account the relative abundances, we see that the average atomic mass of a chlorine atom is 35.4527 atomic mass units. And again, we see that that is the number recorded under the symbol in the periodic table. The presence of one or more additional neutrons in the nucleus of an atom has no measurable effect on the chemical properties of that element, and different isotopes of the same element have the same chemical properties. And this is because the chemical properties of elements are determined by the electrons in the electron cloud, in particular the number of electrons and how those electrons are distributed around the nucleus. When two atoms chemically combine, it is the outer part of the electron clouds that interact. The nuclei of both atoms come nowhere near each other and therefore have no effect on chemical processes. The main difference in the physical properties of isotopes of the same element is the different masses of the atoms, which is the result of the different numbers of neutrons in the nucleus. This effect is more noticeable with elements of low mass or low atomic number, as the differences in masses are relatively much greater compared to the masses of the isotopes themselves. For example, if we compare the hydrogen-1 isotope with the deuterium isotope, the mass of deuterium isotope is roughly twice the mass of the hydrogen-1 isotope.